Hi and welcome back. Today I will continue my tutorial on running a person detection model on a microcontroller. Here you can see once again the diagram of a full chain. In the first part we have covered the part on the left and you can find the video here. It was a data collection capturing images with the OV7675 camera, preprocessing, augmentation, resizing, color and range adjustments, model training, building and training a convolutional neural network. For today we will focus on the part on the right, model conversion, deploying to the target and running inference. Our training script saves the model as model.keras. We could continue in the same script, but that would retrain the model every time. Normally, machine learning models need a lot of compute power, but since our model is small, we can run it on a microcontroller. The catch: microcontroller cannot use TensorFlow directly. So we convert it into a TensorFlow Lite model stored in a flat buffer. Flat buffers are Google's efficient binary format. They let us read data directly from memory without parsing, which is perfect for low latency, resource or constrained devices. This workflow is usually enough to run on platforms like Raspberry Pi, but we need two more steps for smaller embedded systems. This is quantization and converting to CRA. While converting to TF Lite model, we need to quantize the activations, weights, as well as inputs to int8. Since our target device has computational and memory constraints, it is crucial to transform the trained model into something more compact. Inference runs faster because all computations use lightweight integer arithmetic. This common technique transforms 32-bit floating point values into an efficient 8-bit integers. As a recap, at the beginning we had unsigned integers of range 0 to 255. Then we normalized to floats from -1 to 1, and eventually we quantized to -128 to 127 integers. The computation is very simple with the use of scale and 0 point. Finally, we need to convert the model, saved to TF Lite, to C-byte array with XSD, which you can get in this way. Why the extra conversion? On microcontrollers, there is usually no operating system or file system, so you cannot just load a model file. Converting it into a C-byte array lets us embed the model directly into the code and run it without extra libraries. I created a new script, use_model.py. This is what we do here. Load the trained model, initialize the TF Lite converter, and those are the parameters. Representative dataset. You can notice here a new thing. Let's talk about it for a moment. Generating a representative dataset is crucial to avoid accuracy loss when converting to 8-bit. The converter analyzes sample inputs to understand the distribution of values and choose optimal quantization parameters. Around 100 samples taken from training or test dataset are typically sufficient. Please note that we need to ensure that the images must be processed in the same way as those used for inference. Notice here an explicit NP float 32, even though dividing by 127.5 makes it look like floats, NumPy defaults to 64-bit floats. Since our model was trained with 32-bit floats, we convert explicitly to keep everything consistent. Let's continue on the parameters for a converter. Next we have optimizations. We use the default strategy, which reduces size and latency while keeping accuracy loss minimal. Supported ops restricts the converter to int8 operators only. If the model uses unsupported layers, conversion will fail. Inference input-output type forces the model's input and outputs to be int8, meaning we must provide quantized input features during inference. and then run the conversion. To prepare the model for being deployed on microcontrollers, save the TensorFlow Lite model as .tf-lite file and convert it to a C-byte array with XXD. So first we save the TensorFlow Lite model as a file, then use the XXD tool to convert the TensorFlow Lite model to a constant C-byte array with the use of convert to C array method. The previous command outputs a C header file containing the TensorFlow model as a constant unsigned char array. Let's have a look at that file. We will need to add this file into Arduino project. I thought it is interesting to compare the models, so let's load the TF-Lite model to the interpreter and allocate tensors, input and output. We will need to quantize our test images, so we need to retrieve the scale and zero values from the input tensor. First, I run our previous model here and then the TF-Lite on the test dataset. Let's check the accuracy and size of both models. Quite a difference, right? Even though we have 256 kilobytes RAM on the Arduino Nano, we need to be careful not to use everything for our model, as there will be no space available to use for the rest of the program. Also, be careful not to fill everything up. It happened to me that I reached as much as 98% of dynamic memory usage. This managed to put my Arduino to some unexpected state, where the program didn't work and the PC didn't recognize the device anymore. Tip: double click of the reset button brought it back to life, and I could flash the Arduino once more. Now we are done with our Python script, and let's think what should happen on the microcontroller. Microcontroller will take images continuously with specified frame per second as grayscale images in the range of 0 to 155. It will then resize and rescale each frame to 96 by 96, normalize to -1, 1, and then quantize to int8. Then it will feed it into our model. We will use it to make predictions, and the output is a probability for two classes, person detected and no person detected. It's time to get to Arduino code. We need to download the TensorFlow Lite library from the repository here. It's not available in the library manager, so it needs to be installed manually. Once the zip has been downloaded in the Arduino IDE, choose Sketch, Include Library, Add Zip Library, and select the file. The package includes 3 examples, including a person detection demo. That example is more of a mock-up. It uses a blank image and doesn't include camera support, but the workflow is there and we will adapt it. Let's have a look at the structure of the example. In the summary, this is what happens here. First, load the model. We load the weights and network architecture stored in the TensorFlow Lite model. Then we acquire and prepare the input data. We convert the input data acquired from the sensor to the expected format required by the model. Then we run the model. We run the model using the TensorFlow Lite interpreter. And in the end, we need to post-process the results. So let's go through it. Here we include the required TensorFlow Lite micro headers, declare globals, runtime handles, model, pointer to the TF-Lite model, interpreter, the TF-Lite micro interpreter instance, input, pointer to the model's input tensor, tensor arena, static memory, declare a global tensor arena buffer to hold all tensors, input, output, and intermediates of size k tensor arena size. In TF Lite Micro, there's no dynamic allocation at runtime. The interpreter carves needed buffers out of this arena during initialization. The minimum size depends on tensor shapes and graph operators. Initialize target method, this is actually just a placeholder. We could configure our camera here. Load model, point model to the flat buffer embedded in model.h. Micro op resolver, create a global TF Lite Micro mutable op resolver to register all operators supported by TF Lite Micro. We need to pay attention that in our model we use max pool and convolution, not depthwise convolution, and fully connected on top of those. Initialize interpreter, construct the interpreter with model, micro op resolver, tensor arena, allocate tensors and bind input output, call tensor allocation, then retrieve pointer to the input tensor. Here just ensure that model expects correct shape. Let's prepare the input. This part is a little bit convoluted as the idea was to provide the abstraction layer. The data gathering happens, or rather should happen, in the file Arduino image provider, and as you can see, it's only a placeholder. Then we run the model. Last thing here is post-processing of the results, which are also quantized. We retrieve pointer to the output tensor, fetch quantization parameters, and dequantize the result. As a last thing, the response to detection is called, which turns a different LED on depending on the inference result. Now, how can we make this run with our model? In the sketch from previous video, we were acquiring the image, scaling, cropping, and publishing it over serial. Let's try to expand on that, adding TF Lite code I just explained. I will first save it as a new file. I placed functions to scale and crop the images in the file processimage.cpp and processimage.h and place them in Arduino library. I also need to copy the C array we previously created and rename the model to the name used in the example. Let's copy the headers and variables first. I will create a few more. I have prepared everything for this beforehand. For input quantization values and score and label to send over serial together with the image. I copy most of the setup. We need to be careful here, as I mentioned before, we need to modify two operators and add a fully connected one. Let's also fetch here quantization parameters for input, tensor scale, and 0 point for proper int8 pre-processing. In the loop, we already have retrieving the image and scaling and cropping. We still miss normalization, quantization, and setting the image to the input of the model. Let's add it here. Here I go through every pixel in the image and perform those operations. Now we are ready to run inference and process the results. I want to send it as a percentage, thus I multiply by 100 and send it over serial port. Also, I change the variables k person index and k not person index to 1 and 0. Yes, I realized that after trying to compile. Please note here that there used to be unsigned int8, which is not valid anymore, only int8. I almost forgot that we need to adjust our script imageviewer.py. I decided to create a new one though. What happens here is super simple. We just open serial port, read 2 bytes, which are values for score and label. Then we read the remaining pixel values. Then we display the image together with score and label. Let's try to run both. And that's it. We have gone through a full workflow, starting from gathering dataset, training, conversion, quantization, embedding into C-array, and running inference on the microcontroller. I hope this gives you a good starting point. I would love to hear what you are going to build. Share your crazy stories in the comments. And thanks for watching.